Particular thanks to Professor Ingo Waldmann for joining us today. Very interested to hear more about your innovation lab, amongst other things. Ingo is the Chief Technology Officer for Spaceflux. I believe you also still managed to squeeze a bit of lecturing in at UCL, is that correct? Um,
Yes.
and is a fellow of the Alan Turing Institute. So, a bit of an artificial intelligence expert, and very much looking forward to hearing what you have to say. We tend to please invite people to put information and questions in the chat while we go along. And hopefully we'll try and make sure we have at least 5 or 10 minutes left at the end for people to pose any questions they might have. But without any further ado from me, I'm going to pass the mic over to Professor Ingo Waldmann.
Brilliant. Thank you very much, and thank you for the invitation to speak. So it's a great pleasure. Yes, so I'm not lecturing now. So UCL kindly put me on a 3 year secondment, which is very nice of them. And during those 3 years, I've joined Spaceflux that I co-founded a couple of years ago, 2 years ago, um, to develop the product and the R&D roadmap and bring all the academic AI shenanigans that I've been doing in astronomy to the company and try build what we now call Spaceflux Labs, which is our R&D department. And I'll talk to you about that in more detail today. Just to give you an overview of Spaceflux, so we are a very young company. We were established in 2022 and have since grown quite rapidly. So at the moment, we're 29 people. By the end of next month, we'll be 32 probably. And there's a team meeting last year and this year, and that's already out of date. So it's going well, and the idea is that we provide optical space situational awareness data from our London headquarters, but we also now just opened an office in Italy, and so we're quite international, which is quite exciting. So our core abilities is, as I said, it's an optical network of SSA sensors, or being an astronomer, I just call them what they are, telescopes across the world, and that's one of them. They're mainly plane wave telescopes, so mostly off-the-shelf equipment that we bring around the world. And the idea is that it's a vertically integrated company, so we get our own data. We have our own data analysis on the edge, and then that is linked up for further analysis into a cloud system, and everything is, robotically driven from the cloud. So that allows us to get some very, very fast turnaround time. So if there's a network, a sensor available, we can turn around data from request to delivery within, usually 45 seconds or a minute, which is great for, if you need speed. That's our current telescope network. So in last year, we had 8 stations. Today, we have 14. We just had first light on the 15th one, which is a SSA infrared sensor that I'll talk about in Spain. And we have the funding for another 10 networks stations for next year, and you can see where they probably will go. So these are our current leads and ideas where we need to go. Especially Southeast Asia is traditionally more poorly covered by optical SSA for us, but also for other networks. As I said, we're very fast in detecting stuff and following it up. And, there's the now infamous Intelsat 33E breakup on the 19th of October, which was a Sunday. So that ruined all of our weekends collectively. And what happened is that the Intelsat, Boeing built Intelsat, broke up, probably an internal explosion that led it to be fragmented into, I think, in the end, 500 pieces that are currently being tracked. We were fortunate enough to be the first ones to be tracking this event. We had our telescopes in Namibia and in Cyprus online, and of course you have to be lucky because it has to be nighttime and all sorts of stuff. But we were the first on site, and it was very, very exciting measurement. So our current capabilities from an optical perspective is, we can do about 2 to 3 centimeters in LEO. Not across all LEO objects, of course, because we don't have the coverage right now. From next year, we'll do a lot better on that. And 10 centimeters in GEO. So we can look at CubeSats in GEO, which is really, really useful. So that allowed us to really push for that sort of sensitivity. But pushing sensitivity is, a matter of the hardware, of course, but then very much the software as well. And that led us, long-term thinking to the conclusion that we actually need have an externalized R&D group that is not fully in the classic agile production cycle, because it works up to a point, but it can be very disruptive, and it doesn't actually allow you to build and focus on prototyping new systems and new ideas in the most effective way. So that's the reason why I joined full time now to set up this Spaceflux Labs, which is our R&D group, which will focus on really TRL 1 to 6. So 6 to 7 being the prototype that's being tested in a workable environment. So we have a test systems there, so we can take individual telescopes offline, and we have a full test site now in Spain. And then once the prototypes have been tested, so then they go into production as per a usual feature that we would roll out commercially. But the good thing about having the labs is that you can run proof of concept studies with industry partners and academic partners and public sector partners very easily and very dynamically. And sometimes proof of concept studies are just that. They are just to prove a concept or a pilot study, and don't necessarily always lead to a product, but they lead to technical consultancy, for example, with our partners, or just trying something new. And it gives us that flexibility to engage critically in these systems. So me being UCL, have a very strong link to UCL, and especially the Center for Data Intensive Science and Industry. Then, of course, we have strong links with DSTL as well, and we're building links, an internship program with Dirac, which is the high performance computing facility in the UK. Yes, and the idea is that we actively engage in research and in academic research as well. So we're sponsoring PhD students in AI for space situational awareness through the UCL Center for Doctoral Training in Data Intensive Science, as I said. We're also in contact with the CDTs in Bristol and Manchester. So, I love UCL, but I acknowledge that it's not the be-all, end-all. And there were many. The UK is very fortunate to have so many centers of excellence in this field, and it's quite unusual, I would say. And we want to really engage with everyone and all networks that are interested in running POCs and actually using our data, because our data is plenty. We have plenty of it, and it's a very good quality. So it's an excellent breeding ground for this sort of work. And provide consultancy as well. So we will set up an internship program. So our first intern will start in Q1 next year. And these will be 6-month internship programs that mainly with the CDTs, but then later on we'll expand that for students mainly trained in AI or data analysis, but not necessarily only, to come in and look at the data streams and what we can bring out of this data in the future. And the idea is that it's open collaboration, and an open collaboration then usually hopefully leads to products. I'm being constantly reminded that I'm not an academic anymore, and I must have a positive byline coming in. So that's fine. Recent project, just to give you an idea of what we're currently doing, is a project with DSTL, with the MOD's R&D department, and we're currently building, or we've just built, a 70 centimeter telescope for them in Spain to do both optical and near infrared observations. And the idea here is that we will do daytime observations for them. So with the near infrared detector, it goes up to 1.7 microns. And as you know, the Rayleigh scattering curve drops off quite dramatically beyond 1 micron. So you can actually do this during the day. So we had first light yesterday. So that's very exciting. I unfortunately couldn't give you any images because they need calibrating first. So that was a bit too close for this meeting, but we'll go forward with that, and it looks very promising. And the idea is that we, on the back of this project, help DSTL to build some of the SSA requirements for SDA going forward. So we've already consulted, helped them with a sort of literature review, and we'll continue to do that going forward. So that's sort of the stuff that labs will be focusing on very actively. And to give you an idea of the some of the more machine learning projects that we have. So one of them is the problem of detecting faint and small objects in cislunar orbit, or just tiny objects anywhere in any orbit really. How do you detect this? How do you pull it out of what is usually a non-Gaussian noise source, basically? Most of this data is assumed to be Gaussian, but in effect, if you're pushing to signal to noise of 1, non-Gaussian noise will become quite important to deal with. And Kalman filters, for example, are quite bad with if there's non-Gaussian noise involved. Trying to predict orbits forward in like a sort of track before detect mechanism, for example. So generative AI, actually, these are all buzzwords and they've been overused, and it's kind of hurt the field a little bit, unfortunately. But they are very, very useful in modeling non-Gaussian and non-linear systems very, very accurately. So, diffusion networks are usually known through Midjourney or what GPT generates now. In this case, it's just a generation of celebrity faces out of the celebrity face data set. But we can use this concept in SDA and astronomy in general very effectively. And it's been used in astronomy for galaxy classification, for example, or cosmic microwave background simulations. And diffusion models in particular are a system of models that is far more stable than previous iterations, such as generative adversarial models or variational autoencoders. GANs are unstable. VAEs are not very good in capturing the nonlinearity of the data. And the idea is that you map, you build a network that maps from a purely Gaussian noise source to a non-Gaussian data source. So in this case, it goes from a Gaussian noise field to a face, and you do this iteratively over small steps. It's basically like solving an ODE over multiple steps until you reach the right level of complexity. And doing this iteratively actually helps the network to learn the underlying data structure very effectively. Now, this is an example of just some data from our New Mexico site, and you can already see there are cloud patches in the data. It's streaks, star streaks, because it's not sidereally tracking. In this case, it's tracking a satellite, and very complex nonlinear background fields. And that is difficult. So there are classical methods of detrending this data, but up to a point. And this is especially important if you go into very difficult observations, such as daytime observations, where you have extremely strong backgrounds that are variable over multiple parameters, such as water column, air mass, sun illumination angle, zenith angle, all of these things. So understanding the background and understanding your noise, your instrument noise, becomes very important if you really want to push for these really low signal to noise observations. And here's just an example of very faint RSOs that we pick up here, here and there, and then compared to the star trails. Yeah. So what did we do? So we extracted 1 night's worth of data and curated it a little bit to crop it to the same size and so on and so forth. And you can already see that from a raw data, so this is uncorrected data, you can already see some interesting artifacts here. So the CMOS banding noise, which is quite common in CMOS detectors. So it's to do with the readout and the AC-DC converter. Different star streaks of several magnitudes, some of them oversaturating the detector in places, others ghosting. So it's quite a difficult data set as it is, but it's not as difficult as modeling cats, for example, or any face for that matter. It's from a machine learning perspective, it's very simple data. It's the complexity of the data is low. The problem is that the signal to noise is also low. But so we fed this into so I built a diffusion model to take this data, and the idea is then you train the model forwards and backwards. So you train it from the Gaussian distribution to your training data set distribution, and then you reverse it back again to the Gaussian distribution. And you do this iteratively over several epochs. An epoch is, it has to be seen the whole data set once until there's a level of convergence that you're happy with. And once that's trained, you basically can generate new data that has the same statistical properties as your training data. It doesn't necessarily mean it looks exactly like your training data, because you're just generating it from a Gaussian distribution. So it's in a way randomly generated. But it has the same underlying statistics. It has learned the nonlinear manifold of the data that you've given it. And that's the important thing. So you go from left to right, the Gaussian to non-Gaussian. And then what do you do with that? You can then use it to actually detrend your real data by conditioning it on the observation. So this is called conditional reconstruction or inpainting, where you take the network and you feed it some new data, in this case the right, for example, and you run the network back into a sort of semi-Gaussian state. So this is maybe 20% back to the full Gaussian distribution. So it smooths out the distribution enough, but gives it enough impetus to understand where in that manifold your data sits, and then you generate forward from that point onwards, and you do this over several iterations. So in this case, 20, because it's a Gaussian process, and then you sum them all up, and basically what happens in the end is that it will create a basically perfect, near perfect flat field for your data, for your conditioned data. So that's the bit below here. And here it's just an example of how it actually works in real time. So on the left is a single instance of this conditional generative model trained on some, conditioned on some data. And in the middle is the cumulative mean of all of these instances together. And you can see that the Gaussian noise starts, dropping off at some stage, because you're following the central limit theorem, and you're starting to smooth out. And what remains is the non-Gaussian part of your data, which is your CMOS banding and your for example, here you can see the star streak. So on the right is the real data, and then you can see the star streak and some ringing effects that creates on the detector. And those ringing effects are real. They're just so faint that you actually can't see them in the real data necessarily. But the network can model them regardless, because it's seen so many of these distributions. And then you can use that as a flat field. So on the left hand side you have the raw data, and in the really faint RSO in the geo belt, signal to noise of 1.5 over the Gaussian background. Your diffusion generated a systematic noise model, and on the right hand side your detrended data. So it's doing good stuff. It's still very early on. It's not in production yet, but we know that generative models can help a lot in addressing local calibration needs. Because you train the model locally on that specific instrument and that specific condition, and it will improve over time, and it will learn the local environment and the local CCD or CMOS camera and all that sort of stuff. So it's not a globally imported flat field that you make, but it's a continuously online learning approach to data analysis. And if you actually then plot a power spectrum of the data, it's exactly, you see what you expect, which is always nice. That the blue is the input data, and you can see there's a lot of power in the low frequency. So this is the non-Gaussian noise that I just discussed, and then you've got the noise map in gray. And if you subtract those two, you actually see a dramatic drop of an order of magnitude in power for the low level non-Gaussian sort of flat fielding errors that you saw in the data. And of course, it doesn't do very well in the Gaussian part here because ultimately it's not supposed to, because a diffusion network is based on an underlying Gaussian distribution, so it becomes quite difficult. And you would probably use something more like a Wasserstein-GAN architecture if you really want to push into the higher frequencies. So what do we do with that as a next step? And I'm nearly done, so we've got some time for questions. Well, once we understand how to model this non-Gaussian noise at a higher precision than what a normal astronomy pipeline would be able to do, you can do a lot of fun stuff. You can make your data more Gaussian, which makes it more amenable to Kalman filters and similar, that assume Gaussianity as an underlying factor. But you can also do other stuff. You can build it into more complex models that model both the data distribution as well as, for example, your RSO's orbit. So track before detect algorithms, for example, that model very faint objects through a data cube of observations, and the third axis being time, without necessarily knowing where the object is initially. And this is where we're currently working on how do we do track before detect very efficiently for very, very faint signal to noise objects. Kalman filters and similar are very good. But what we actually want to see is, these are maximum likelihood solutions. What we actually want to see is a full Bayesian posterior distribution of the modeling solution, given the noise characteristics. For that, you usually need a Markov chain Monte Carlo nested sampling approach, which are they're too slow to run for this sort of high complexity, high dimensionality data. So we are currently, we had an Amos poster on that, exploring simulation-based and variational inference approaches. They're very popular in astronomy right now in certain fields. And amortized neural posterior estimators are very good solutions for this problem that actually allow us to learn the solution space a priori and then apply it to new observations and still maintain sort of full Bayesian solution accuracy. So it's a formal Bayesian machine learning approach that is quite important if you actually want to understand your uncertainties in your model solution and in your data. Being Bayesian is not a bad thing. So so that's just a very brief overview. And I've got 5 minutes time. So in conclusion, basically, Spaceflux here, we're open for business. We've got a global telescope network, and we do want to foster this sort of work. especially in collaborations with, relevant networks, such as this one, of course, academic partners and industry partners, because we do believe that this is the way forward to actually, push new ideas out and develop them. So thanks very much, and happy to take any
Thank
questions if
you
you have
very
any.
much, Ingo. That was really super interesting. People talk a lot about applying AI tools and techniques to these vast data sets, but it's great to see how that's actually working in practice and explained in a way that even somebody with my level of technical understanding could follow. There are a couple of questions that have come in. One from Angela Matisse, Think Tank Labs, asking, as an academic and or private company partner, do you charge partners for a fee to access and use your data? May not get in time to get into the details of terms and conditions, but question is, do you charge? And also a question here from James Blake about how much of your observation time of that whole expended network would you dedicate to kind of general surveys versus bespoke monitoring for specific, I guess, partners who are paying you to do that. Two questions there. I have a whole bunch of questions, but I'm going to let you answer those first.
Great. Yeah. Yeah. Thank you for those questions. That's a very, very good points raised. So yes, so we do charge for data because we are a company and we have to pay salaries. But of course, it depends on what data. So historic data will be a completely different price point to, having your data turned around in 30 seconds. Um, we're currently developing a pricing model for historic and R&D data sets because we had quite a few requests like that. And I think it's a good thing to have that is not prohibitive in the pricing. And the other one, yes, that's why we're expanding the telescope network at the moment, where we do surveys as well, of course, but we are expanding with more of these 30 to 70 centimeter telescopes, as well as lens arrays and daytime monitoring in the next year. So that gives us, more and more capacity to actually, service larger surveys, and especially geo and MEO belt.
It's a one question for me, and congratulations on getting your daytime observations up and running yesterday, I guess, hot off the press. Um, will you be working on fusing those data sets, the optical and the RF? Is that part of this project?
Yeah, exactly. So exactly. We have a few pilots on the fusing radar, RF, but on the sphere, definitely the optical. I mean, it's in a way it's almost standalone because just getting TLEs during the day, TDMs during the day is really important for maintaining custody of orbits. But it's exactly that, and spectral fingerprinting is of course very interesting because you start getting some interesting signatures in the infrared that allow us to do cool stuff with that. So yeah. So
Great. If anyone else has a question, feel free just to click the raise your hand button. We have a couple minutes left. In the meantime, two thoughts were triggered for me. One is so your innovation lab has started in Spain. Did I understand that correctly?
no, it's in the UK. We just
Oh,
have a
okay.
test site in Spain
Okay.
because London
Because I was
weather
going to ask
isn't
you
that.
why Spain, but anyway, so that's good. I
It's the
just
closest nice space.
Um, you mentioned 2.5 centimeter object detection, I guess. I don't recall whether you said and monitoring. Um, do you see a market for 2.5 centimeters? It's always the great debate amongst the GNOSIS community. It's really important for debris. Is there actually a commercial application for monitoring down to that size?
Oh, that's a good question. I hope so.
Yeah, I
Um,
hope so too. But you're not seeing interest from buyers
No, not
yet. Okay.
immediately, but it's more like what can we actually see rather
Yeah.
than
Yeah.
um but yeah, hopefully we'll get there as a community.
Yes, here's hoping. Okay, well, thank you so much. I really appreciate it. We've run out of time, but I assume people know where to find you, and you are on LinkedIn. If anybody has any, questions that comes up after the lunch break. Thank you very much. I really appreciate it. And look out on the GNOSIS newsletter and the website for our next GNOSIS Connects. We have a series coming up over the coming months. Thank you, and have
Brilliant.
a great rest of your day.
Thank you very much.